Greetings, the Astro 30 here, and welcome back to AEL. And if you're new to this channel, please consider going down below and subscribing. That'll help me out immensely. Now, today we're going to be looking at another 555 timer circuit. I know I don't want to turn this channel into the 555 channel, however, it still today has many uses. Today we're going to be looking at a variable motor speed controller. Now, there are different and better ways of doing it other than just using a 555 timer, but it's what I have to work with anyway. I've got plenty of them, so I might as well experiment with them. And that's what this channel is about, is experimentation. Now, the circuit we're looking at, which I will link down in the description below, this original use was for controlling a wiper motor on an automobile, so you could vary the sweep rate of the windscreen wipers. But it does have other uses other than that. The way they've got this configured is they've got it configured in off-stable mode. So we're varying here at pin 7, which is the discharge pin. We're varying the total resistance here and here between the capacitor here. So we're changing the charge constant of that capacitor, which is controlling pin 2 and pin 6. That would also control our frequency, so it would either increase the frequency or decrease the frequency. What the purpose of this diode here, which is a 1N4148 between pin 7 and, well, the bottom of the pot, I'm not actually sure. It doesn't actually say in the description below. However, what I think they're trying to do is we're trying to ignore the discharge signal when this output is high, because that then brings this discharge pin to ground, so it helps to discharge this capacitor so it can go back into the next cycle. So they're basically trying to ignore that through here and only have the positive supply going through to the capacitor, I think. Other than that, I'm not really sure what it's for. I don't have any 1N4148s, so I'm going to just use a 1N4004. It's really irrelevant. They've also got the positive supply rail to the IC DC decoupled through this 10 ohm resistor and this 470 microfarad capacitor and 100 nanofarad capacitor respectively. I believe that's to isolate the oscillator from the output stage over here. The other thing I don't like is pin 3 is directly driving the base of this BD239, which is a 220 device. I don't have one of those. I've got a BD139. I looked at the data sheet for the 239 and it's 115 volts for the collector to emitter voltage and 2 amps, whereas the BD139 is 80 volts collector to emitter and 1.5 amps. However, I think that's overkill there, because it's actually connected in Darlington configuration with this output transistor, which is a BD249, which I also don't have. But because of the use of this circuit was for controlling a wiper motor in a car, or van, or any vehicle for that matter, well, those motors, when they're under load, can draw nearly a couple of amps. So you want a pretty beefy output stage. They've got the collector of this with a little bit of degeneration with a 68 ohm 2 watt device. Now, I don't have a 2 watt 68 ohm. I have a 120 ohm 2 watt, so I could probably use that. However, for my testing purposes, I'm not going to worry too much about having this output stage in Darlington configuration, because the only motor I've got is a fan motor anyway. So I'll just use a BD139 instead, get rid of that resistor and bring that straight to the positive. But I'll still include this DC decoupling here. However, I don't have a 10 ohm 1 watt device. I do have a 22 ohm 5 watt device. So I might use that instead. I don't think it's going to make that much of a difference to the circuit if it's 22 ohms. So I guess what I'm going to start with first is I'm going to build up this part of the circuit without the output station. I'm just going to scope what the output is doing so I know what the frequency varying is. They're using a 47k pot here for VR1, which is a non-standard value. So I'm just going to use a 50k. I've got one of them. And yeah, all the other resistors it looks like I've got, which is 1.5k. I mean, that's it. It's only like 2 other resistors. And I'm not going to worry too much about this resistor and LED over here. It's not relevant to the circuit anyway, so that can be omitted. So, alright, so I'll get to building up this part of the circuit and we'll see how it operates. Okay, so I've got the oscillator circuit built now. I did actually have a 10 ohm 1 watt resistor, so that's what I'm using. I'm using a 100 microfarad instead of a 470. I don't think it's going to make too much of a difference in this test. Now, I was originally using a 50 kilo ohm pot in the circuit, but for some reason it started to oscillate once, and then as soon as I rotated the pot, it stopped oscillating. So I've now substituted it for a 10k, but I want to find out the reason for why that pot is not allowing the circuit to function. So I've got my multimeter set up, so I'm going to just measure across the center wiper and the upper or clockwise position of the pot. And it's, even with the pot in the center, we're like at 126 kilo ohms, which is completely incorrect. If I rotate it fully clockwise, we're now 95 kilo ohms. And if I wind it all the way down to counterclockwise and then measure the resistance, we're still at 145 kilo ohms, which is completely wrong. So if I measure the counterclockwise to wiper, again it's 95 kilo ohms. If I wind that back up to the center, well, if I could get a good connection, 125. And if I wind it all the way clockwise now, 145. There is something wrong with the pot. Most likely the wiper is starting to go open. I believe this pot was used in another experiment where I had it wired incorrectly and I was putting DC through it and a little bit of smoke came out. The pot did work for a while after that, but it appears that it's not working properly at the moment. So I might have to buy another one, but that's alright. So back to this circuit and testing it. Now let's have a look at the oscilloscope screen, because I've got that connected to pin 3 and ground. Now I still do have trouble focusing on this TFT screen, so I'm going to leave the iris low for this so you can see it better. I'm trying my best to make my material a lot more pleasing to watch and easy to read. So currently the 10k pot is sitting in the center, and well, we've got a frequency of roughly 912 Hertz. So what I might do is I might put on the duty cycle instead for the RMS voltage where it was before. So now we can see that we're at roughly 57% duty cycle. Now if I rotate the pot from center to fully counterclockwise, the frequency has increased a little, and we're now at 89% duty cycle. If I now rotate it back the other way, and we can see the PWM is actually changing. If I rotate it fully clockwise, we're now at 23% duty cycle and 969 odd Hertz. So I'll put it back in the center. It's almost 50% duty cycle. So that is an interesting result, but it does kind of make sense because we're varying the resistance between discharge and the threshold pins, which if you change the resistance values, like the resistor value between the positive and say discharge, and you have a greater resistance between discharge and threshold, well, you're going to change the duty cycle as well as modify the frequency slightly. I actually initially thought that the frequency would be varying, but no, it's the duty cycle. Oh well. Next thing to do is to build an output stage so we can actually connect it to a motor and see what it does. Got the output stage now, well, one transistor anyway, connected. I forgot to mention the purpose of the 100 nanofarad capacitor across the snubber diode here is to try and remove some of the high frequency noise off of the motor. So I've got the fan connected. Let's turn the supply on. Well, it works, but immediately we've got that noise of PWM on the fan motor. If I vary the pot, that's the slow speed, but I've obviously got the pot wired backwards. Yeah, so that 100 nanofarad capacitor, if I even pull it out of circuit completely, does absolutely nothing. Okay, time for big old faithful to go into the circuit. If I can do this. So the negative goes that side, and that goes to the emitter. And if I can get it to stay in there, which I can't, there it is, the noise goes. However, the speed is not really varying that much. Could be because this pot is too low of a value. So what I might do is I might swap it to a 100k, which I have just handily here, and see if that makes a difference to the circuit. Right, the 100k pot is in, so I'll turn the power supply on. Fan spins up. I'm at minimum resistance. I've swapped the wires around on the pot. Now, I'm only drawing 150 mA instead of the 200 mA this fan should be drawing, so I don't think this is operating at full speed either. And I think the value of this pot is too high. It should be 50k, but I don't have a working one. So I think our output voltage is not quite the full 12 volts. Yeah, it's not. It's only about 9.8. So I think the transistor is being driven too hard. So I might want to put a resistor in between the base and the output of the IC. Yeah, well, I did some experimenting off the camera there, and yeah, I can't really get it to go close to full speed unless I change that 100 nanofarad capacitor to a lower value such as a 220 picofarad, but then it doesn't maintain the low speed, which is kind of annoying. So currently we're going from 146 Hertz roughly at 3% duty cycle, and 138 Hertz and 98% duty cycle, and we're roughly getting 10.3 on the output. I also have a TIP35C connected in Darlington as in the original circuit with the BD139, and just a 220 ohm 2 watt resistor there between the collector and positive of the BD139. Now it seems to work. However, let's do that experiment with the changing of the capacitor. Fan speeds up a bit, so I'll go between there and, if I can get it there, come on. Right, the fan speeds up. We're at about 11.4 volt now, which is much more closer to the 12 volts, and I need to change the time base on my scope. Other way. There we go. So we can read the frequency. There we are. We're at 38 kilohertz now, and 98% duty cycle. slow it down, and we're at 30% duty cycle and 298 kilohertz. So yeah, it doesn't spin as slow with that capacitor in. And there seems to be an issue at the bottom end of the pot here, where it does that and then comes back up again. I'm not sure why it's doing that, but anyway. So yeah, it is going faster, but it's not perfect. Is this circuit practical? Not really. However, is it fun? Yes, it is. So I'll take that capacitor back out and I'll stick the 100 nanofarad back in. So for this circuit, that's about the best I'm going to get it. It's 10.3 volts at the maximum output with 12.5 going in. So if you up the voltage a little, you can compensate, but then again, that'll also affect the low end speed as well. So if I put it on the low and I up the voltage in, it's about 13.6, it brings the voltage up at the low end as well. But we're at 11.5, which is closest to 12 volts that we need. And if it was running in a car, well, then yeah, it would work effectively, because that roughly when the engine's running, that's going to be close to 14 volt. The circuit works, however, it's just not that practical. And it's not a very low speed either. So, I mean, if you messed with the capacitor values and resistor values here, and I was actually using a 50k pot, that would give a much more precise control over it. Then yeah, it probably would be a little bit more practical, but for what it is, yeah, it works. So, a bollocks to that circuit. However, I will say I was not using the original output transistors as specified in the original circuit. So my test results may vary wildly compared to how it worked when he built it. So without actually testing it with the proper output transistors that were specified in that particular build, I can't really realistically condemn the circuit as non-viable. However, having said that, I have now come up with my own implementation which works more satisfactorily than that one did. So we still have a 555 timer here, and it's configured in a stable operation, and with the values of this 10k, the 5k6 and the 100 nanofarad capacitor here, that gives us roughly a operating frequency of about 6.8 kilohertz, somewhere around there. And on pin 5, the control voltage, we're varying that voltage, which is going to vary the duty cycle of the square wave. Keep in mind that when you vary the duty cycle of the square wave, the frequency at the output is going to vary. So the basic operation is, when this pot is rotated fully anti-clockwise, well, the control voltage is 0, therefore the output is 0. As soon as the pot starts to increase in its rotation, the control voltage starts to increase and the duty cycle starts to change. And we go from a duty cycle of roughly about 3%, and when the pot is rotated closer to maximum, the duty cycle will increase to roughly 99%, and when it reaches maximum, when the control voltage is the same as the supply voltage, well, the duty cycle then becomes nothing, or 100%, and the output is constantly high. This 9.1 volt Zener diode over here and this capacitor together with this 200 ohm resistor, that just helps keep this IC stable, especially when you're driving a motor that has brushes in it, and you want to just make sure that the spikes and nasties that are happening because of the commutator inside the motor doesn't affect the duty cycle operation of the circuit and doesn't vary its speed because of the spikes. And it also allows this IC to run at around about 9 volts with a higher supply voltage than 12 volt. Say you wanted to run an 18 volt motor, well, you could put 18 volts here and this IC will still see around about 9.5 volts. So you will not exceed the VCC maximum of this circuit IC, which is 15 volts. And the output of pin 3 goes through this 33k resistor and this 100 nanofarad capacitor. This just forms a low pass filter, and it just removes any high frequency nasties that might be on the output there because of the feedback from the motor going into the supply lines, etc. Just to keep this output transistor stable. Now I'm using a BD681, which is a 100 volt collector to emitter, 4 amp current capability Darlington transistor, and without this capacitor installed, when you rotate the pot no more than, say, a third of a turn, the motor is running at full speed already. And increasing this resistor any higher than 33k, and then the motor fails to turn on at all. So adding this capacitor in here between the base and ground just helps filter the output and keep this transistor stable, so it does actually work and control the speed of the motor over a linear range of the rotation of the pot. Another thing about this transistor is I've now moved it to a common emitter. Before, in the original circuit, it was a emitter follower basically. That is, the collector was connected to the positive and the load was driven off of the emitter. Now I found that if I swapped the emitter and collector connections around, that is, the emitter went to ground and the motor or the load went to the collector side between that and the positive rail, we didn't have that voltage loss that we were experiencing before. Remember, in the original circuit we were only getting to around about 10 volts at maximum speed. Well, the BD139 that I was using wasn't happy in the emitter follower configuration, driving the load through its emitter. This transistor I haven't actually tested in that direction, whether it would make any difference, but I'm going to leave this as a common emitter because, well, it works fine. Why change it? So let's look at this circuit now on the breadboard and take some measurements and see how it operates. So there's the new circuit built there. I've got the power supply turned on, but the load isn't connected at this stage. So I'll just turn the supply's load on. Nothing happened. I'm also using just a 100 microfarad capacitor across the motor instead of 1000. And for this particular circuit, it seems to work okay. There's a little bit of noise there. And the fan starts spinning slowly, but we're at roughly halfway of the rotation of the pot. And there's full speed. And with the supply of 12.4, we're getting about 11.2 out, which is a lot better results than the last one. So if we rotate it to minimum, well, we end up with naff all there. So if we look at the scope screen, I'm scoping the output of pin 3. There's our duty cycle, but I need to increase my time base a bit. Now at the lowest we can see it's 15% roughly and 1.2 kilohertz. So I'll increase it to half speed, which is half voltage, which would be roughly about there. Right, well, we're not at 50% duty cycle, so let's make it so we are at 50%. Right, so according to that, at a 50% duty cycle, we're actually at 1.3 kilohertz. But anyway, we can see that it is actually working. However, at 50%, the fan's not actually rotating. So I might make a quick little change to the resistor going to the base of the transistor and see if we can get this to operate a little bit more smoothly. Okay, so I went back to a 10k pot and I changed the base resistor to a 22. It seems to work a little bit better. So Just the annoying point is most of its speed controlling range is in the very lower portion of the pot. I guess that's alright, especially if you want to control a drill motor, for instance. And it does have quite a bit of torque behind it. So I think that's where we're going to leave this little experiment today. My version works a lot better than the other one did. So I'm happy about that, and I think this actually does deserve a PCB. What do you think? Leave your thoughts below. So anyway, I'm going to leave this video here, and I hope you enjoyed it. If you did, please remember to go down below, like, comment and subscribe if you haven't done so already. And anyway, as always, this is the Astro 30 saying, see ya, have a great day.